Hello students, in the last video we have discussed about Greeback normal form. In this video we will discuss about pumping lemma for context-free languages. So what is pumping lemma? Let me recall the pumping lemma of regular languages. See, pumping lemma is generally used to prove that a language is not a regular language. So if some language satisfies the pumping lemma, then it may or may not be regular, that I cannot tell it. But if a language does not satisfy the pumping lemma, then we can conclude that that language is not a regular language. If it is satisfying, we cannot give any conclusion, but if it is not satisfying, we can prove it. Same way you can go for CFL also, but the statement of the pumping lemma is different, that's it, right? So we have to take a different statement for the CFL. Now in finite automata, we have to pump a variable. What is the need of this pumping actually? See, if the language is infinite, but you want to represent in a finite number of states, then there must be something which is going to be pumped, right, or should be taken infinite number of times. If so, then only we can represent the infinite language in the finite number of states. Otherwise that is not possible at all. So if you're having like x, y and z, then this y has to be pumped any number of times. And what are the restrictions and conditions for this x, y, z we have discussed in the regular language. So in the same way, for the context-free languages, okay, so we are going to have some dependency, right, for the context-free languages. So like if you take this language, this is not regular, we have proved it, a power n, b power n, such that n greater than or equivalent to 0. Means, let me take this, okay. Sorry. Yeah, let me take this language L equivalent to a power n, b power m, c power q, d power m, e power something like, okay, r, whatever it is, all greater than or equivalent to 0. Now see, the b is dependent on d, or d is depending on b. So if I take two b's, I must take the two d's. No need to worry about a, c and e. But if I take three b's, I must take the three d's. Because if it is dependence is there, this is not regular. And if one dependency is there, this is CFL. If that dependency is possible with this, then we have to take. So there must be some variables which are on dependent. Here I am saying that, for example, v and x, you can take it. V and y or x. There must be some variable which are dependent. So if I pump 2 times, this should be pumped 2 times. 3 times, 3. Like that. So, and I'm not worrying about the remaining variables like u, w, that we can take any number of times, or y we can take. So now if I pump this 2 times, this must be 2 times, so that the strings must be in the language. If you could able to identify such v and x, the pumping variables, and for all those pumping, if it is in the language, then we can conclude that the language is CFL. So for that, so here we are pumping only one piece, but here we are pumping two pieces or two variables. That's what exactly the CFL. So the CFL pumping lemma is little more complicated because we have pumped only one variable in regular, but here we have to pump two pieces of any string. So repeat each of two pieces in the same number of times, we get the another string which is in the language. If you are not getting it, then definitely it is not satisfying the lemma and it is not language. So here we are having pumping lemma statement. Let me recall the pumping lemma statement for regular language. There must be some n, assumption only, which may be depending on the number of variables or states, can say that. Then you have to take a string which is greater than or equivalent to n and divide this string into three parts, x, y, z, such that the length of the xy should be less than or equivalent to n and the length of the y should be greater than 0. So for all I, x, y power I, z should be, the pumping of y variable should be belongs to the language. Otherwise, it is not a regular. Same concept here. First you have to assume n, then that should be less than or equal, greater than or equal to n, but divide the z into, the string into 5 parts. Here we have 3, right? 5. Then same way, the first VWX, this one should be less than or equivalent to n. Here XY, okay, but here VWX should be less than or equivalent to n. And here the pumping variable should be greater than 0, right? Here what are the pumping variables? V and X are the pumping variables according to the earlier diagram. V and X, those should be greater than 0 together. No need to worry, that together should be greater than 0. In that case, there is no restriction on U, there is no restriction on Y. The restriction is only on VWX and VX. So for all I greater than 0, U V power I W X power I Y should be in the language. If not, then it is not going to satisfy the condition. Let me explain the same thing with the diagram here. So divide the whole string into U, V, W, X and Y. You can even apply it for the regular language also. So by taking only the half of it, this part, don't take this, like, okay, already they have given, right? By assuming this part, you can assume the same process for the regular languages also. Okay, they have already given this part, right? So U, V, W, X, Y. So the conditions only on V, X, Y should be less than or equivalent to n. And this V and X together cannot be epsilon. That's what we have taken. And if I pump this 0 times, okay, you'll get like this. Pump 0 times, U, W, Y should be in the language. Pump it 2 times. This yellow color should be pumped 2 times. U, V power V square, W, X square, Y should be in the language. If I pump 3 times, U, V cube, W, X cube, Y should be in the language. Let me explain this with a simple example, guys. Here we are having the language A power I, B power I, C power I. So what are the strings in it? You can take epsilon, A, B, C, or you can take A, B, B, C, C, or you can take triple A, triple B, triple C, so on like that. So now if you are asked to say that whether it is CFL or not, then you have to construct the PDA, so that we have to take A's followed by B's followed by C's. Okay, I'm not worrying about which operation you are performing. Then we need to assume that the number of states is 3. This is completely assumption only. You can construct a PDA of any number of states. We have discussed that should be only one minimal automata. We have discussed that. So we are just assuming that the minimum states or assumptions is 3. Then take any string Z which is greater than or equivalent to 3. So let me go with 6, right? A, B, B, C, C. So the length of this Z is 6, which is greater than or equivalent to n, satisfying the condition. And we have to divide now. We have to divide this string into 5 parts, right? Such that the length of VWX, is it so? Yes, right? So now this VWX should be less than or equivalent to 3. You have to do like that. So you cannot take it as a 4. Just go with this, right? VWX, the condition is on VWX should be less than or equivalent to 3. So I'm saying that this is VWX. And automatically this is U and this is Z. There is no condition on U and Z. You can take directly U is epsilon also. No problem with that, right? So now you can take, for example, you may get a doubt that can't we take Z is epsilon, U is epsilon? Yes, there is no restriction at all. Let me go with this. Now what is U here? A. So what is VWX here? ABB. And what is Z here? CC. And again we have to divide this VWX as VWX, but the condition is VX together should not be greater than should not be epsilon. So I'll take this as V, this as W, this as X. So what is a VX here? It is nothing but AB. Of course length of VX is 2, then that is greater than 0, no problem. You can take V is epsilon, X is B, or X is B and X is epsilon, V is A. That's your wish, right? Then now we got everything, like what is U here? A. What is Z? CC? What is V? A. What is W? B. What is X here? B. Then you have to take for all I. So Z means, sorry, U V power I, W X power I, Z should be belongs to L. Let me take I equivalent to 1. You can start with the 0 also, but let me go with this. U. So what is U here? A. What is V here? A. What is W? B, what is X, B, what is Z, C, C. It is belongs to L. A, B, B, C, C, S, whatever we have taken. I equivalent to 2 take U, V 2 times W, X 2 times Z. So what is U here? A, V 2 times. What is V? A, you have take 2 times. What is W? B 1 time. What is X? B take 2 times. What is Z? C, C. See, number of A's followed by equal number of B's but not followed by equal number of C's. So this is not belongs to L. Then we can conclude that the language is not contextual language. So one dependency can be possible with the CFL, number of A's followed by equal number of B's. But if you have one more dependency, that is not possible with the CFL. So that's why it is not satisfying the pumping lemma. If it is not satisfying the pumping lemma, then you can conclude that the language is not a context-free language. Right? So in the next video, we'll discuss about closure properties of context-free languages.